In this video, we're going to look at the magnetic moments of certain nuclei. So we're going to start off by looking at a magnetic dipole. We're going to denote by the symbol mu. And so this is our magnetic dipole. And let's imagine we have the situation here. We have a charged particle, such as a nucleus, which is orbiting around a central point in a fixed path, and we're going to start off assuming that this path is circular and then generalize later. But this is effectively a system which has some sort of angular momentum, and for nuclei, their spin has an intrinsic angular momentum. It's not exactly like it rotating around a central point or like it rotating around itself, but nuclei do have this intrinsic angular momentum, and this is sort of one way which we can think about visualizing that. So this magnetic dipole, whenever you have a situation like this, is going to be equal to the current, which is the charge passing through a cross-section per unit time. So the current times the area of this path that it makes. So if we look into this a little bit further, we know that current is equal to charge over time. And we know that that's going to be the charge of whatever nuclear particle we have here. If it's a proton, then it's just plus times the charge of the electron. And then divided by the time it takes for us to complete one complete revolution here. So that's going to be the velocity of our particle divided by the length of our path, which is 2 pi times the radius. So the diameter of this circle is 2 pi r, and its velocity is v. V divided by the diameter gives us 1 over the time that it takes to complete this loop. So that gives us our current. Then we want to get what the area is, and the area of this, it's just a circle, so the area is pi r squared. So we take these two and we multiply them together, I times a. That gives us that mu is equal to, well, if we put them together, we get qv over 2 pi r times pi r squared. And then this pi is going to cancel out with that pi. This r squared cancels out the r on bottom, leaving 1 r on top. And what we get is that mu is equal to charge times velocity times radius over 2. Okay, so that's for a circular orbit. So that's for a circular orbit, and we can generalize this by going to the more general case of saying it is the charge over 2 of the radius, the r vector, so the vector from the central point to our particle, crossed with the velocity. So we have r cross v there, which is true for any kind of general path orbiting a central point. That's our general path. That doesn't have to be circular. And we can break this down further because we know that momentum is equal to mass times velocity. So that means that r cross v is equal to 1 over m times r cross p. So the momentum is m times v, so r cross p is m times r cross v. So if we divide by m, we have r cross p there. And then this r cross p, we also know that r cross p, so our radius vector crossed with our momentum vector, this is equal to the value of angular momentum, capital L. So angular momentum is our radius vector crossed with our momentum vector, gives us angular momentum. So substituting this back in here, we now have that our magnetic moment mu, that's going to equal charge over, sorry, this was a 2 down here. That was incorrect. Make that a 2. Very bad 2, but a 2 nonetheless. Okay, so we've got Q over 2, which comes from there. And we have the M from the denominator up there. And then R cross P is going to give us L. You should be able to work through the algebra of how we got from there to there. And now what we do when we go to quantum mechanics is we're going to go from this kind of magnetic moment vector and our angular momentum vector to these are going to be represented by operators going to quantum mechanics. So we're going to have mu hat, our magnetic moment operator. This is going to equal charge of our nucleus divided by 2 times the mass of our nucleus times our nuclear spin angular momentum operator, I, from the previous video. Okay, so that's our magnetic moment there. And there's also going to be another proportionality factor that comes out front. When you get down to the quantum mechanical level, when you get down to the spin of a single nucleus, there's actually another proportionality constant which depends on each nucleus, and it multiplies this value by a constant scale factor. And it just depends on the properties of the individual nucleus. This is going to be this constant Gn here, which we're going to put out in front. Okay, I'm going to explain this more in a second. So if we put this out here, this is also equal to Gn, and then this factor Q, the charge of the nucleus, over 2 times the mass of the nucleus. This is also called the nuclear magneton beta. I'm going to write that down in a second. Then this is times the operator I. And then this value of G, the nuclear factor, times beta, G the nuclear factor times beta, the nuclear magneton. This is going to be a value called gamma times the operator I. Okay, so let's unpack what I just said there. So we had beta N is called the nuclear magneton. And beta N is equal to the charge of the nucleus over 2 times its mass. And then we have another value which depends on which specific nucleus you're talking about, Gn, which is called the nuclear factor, which is just a values for each specific nucleus. So H1 has a different value than H2, carbon-13 has a different value than both of those, and carbon-12 has a different value from all of those. Each individual nucleus, depending on its number of protons and electrons, has a different value for Gn. And then finally, this last value here, gamma. Gamma is equal to the nuclear factor times the nuclear magneton, which is of course equal to Gn times Q over 2Mn. And this value is called the Magnetogyric Ratio. So gamma, our magnetogyric ratio, tells us for a given magnetic moment, mu, for a given magnetic dipole, how much of an angular momentum do we have. So for this magnetic dipole mu, how much of a nuclear spin angular momentum do we have? It's this proportionality factor in between these two operators here for our magnetic dipole and for our nuclear spin angular momentum operator.